All right, so if simple linear regression is great with one variable, why not do it with 2 or 3 or 4 variables? That brings us to multiple regression. So linear regression, we just had this, and we fit a straight line. We regressed y on x. So why not incorporate more variables? Let's set up our assumptions just like we did before. And so we're still going to assume normality, except now we want that this is for fixed bunch of x's. So this might be, what did we have? We had gestational age. This might be birth weight, and so on. This might be the mother's age, and so on. Bring in all those factors. Then for a fixed set of those, we're going to have a bunch of y's, and we're going to assume that they're normally distributed with a particular mean, and the mean is going to lie on a straight line, and then we're going to have a standard deviation there too. So we're going to assume that the mean is linear in all the x's. So whereas before we fit a straight line, now we're going to fit a plane. Big deal. But this is important. We're going to retain our assumption of homoscedasticity. So we have to assume that if you give me a fixed set of x's, the y's that vary around that mean all have the same standard deviation. So that's the homoscedasticity assumption. And once again, that the y's are independent. So it's the same assumptions as before, except we're talking about a plane instead of a line. All right? No big deal. And what we're going to do is we're going to minimize the sums of squares of residuals again. So we're going to do the least squares fit to these data, just like we did before. And once again, Stater knows how to do this, and the Gauss formulae work here and everything. So here is an example of this. Now, instead of saying regress head circumference on gestational age, we now say gestational age and weight. So this is birth weight to see whether that helps us or not. So here are the coefficients now. And so that's the coefficient for gestational age. It's 0.45. And that's the coefficient for weight is 0.0047. Now, these coefficients are not, they're not unit independent, because the head circumference was measured in centimeters. So the 0.45 times gestational age was in weeks, so the units for 0.45 has to be centimeters divided by weeks. All right? And so here, for example, this is 0.0047 times weight in grams. So that's why it's such a tiny thing. It might be very important, but it's tiny because we're measuring the baby in grams. Okay? Had we measured the baby in kilos, then we would have to divide this by 1,000, and it looks much more impressive. Okay? But anyway, so we did it in grams. And now, so there are the coefficients. There's the line. Once again, there's the standard error of the residuals. We can compare that standard error to when we just did the one variable. When we just looked at gestational age, then that standard error was 1.59. So we've reduced it. So these kiddies now are much more homogeneous as far as head circumference is concerned when we also bring into the argument their weight. Okay, what did they weigh in at when they were born? That is going to help us in predict the head circumference a little bit better than before. I mean, we're at 1.3 instead of 1.6, so what is that? Another 20% reduction in the standard deviation. Great. All right. Now, let's look at these coefficients again. So there they are, and here are the standard errors, and there are the t's, and there are the p-values associated with these coefficients. So each one of these t's is highly significant, less than 0.05. In fact, each one of them is less than 0.0005. Okay, so they're all less than 0.05. So they're all significant. In fact, had we, once again, if we use the confidence interval argument, we see that none of those confidence intervals includes the 0.0, and so we would reject the null hypothesis that any one of these betas is equal to 0. The other thing is, remember the r squared before with just a single one. When we did this thing, the r squared was something like 0.6, if I remember correctly. Now it's gone up to about 0.75. I would recommend looking at the adjusted r squared. It tends to be a little bit more realistic because it's accommodating the fact that you're estimating, you're bringing in more covariates. So it's a little bit cleaner to look at the adjusted r squared. But anyway, they're both at around 0.75. So that's how you do multiple regression. Now, the only problem with multiple regression is that the way we've done it here is we've acted as if they are additive. Gestational age and weight are additive. What about, could there be some interaction between gestational age and weight? This is the problem when you start with multiple regression. We'll come back to that in 1 minute. But first, that's it for multiple